you going to connect? Let's see. Yes. Alrighty, we're working. So, good morning, everybody. Hopefully your weekend went smoothly. I was taking a look at our poll this morning. It does look like most of you want to do the exam the Monday after spring break, and that's fine with me. So, let's go ahead and we'll plan for that then. So I'll just kind of start with that. So exam 3 will be Monday, April 5th. So we'll have that there. So with that in mind, it's just going to be chapters. Let's see, 6, 7, 8. That's going to be on intermolecular forces, gases, and solutions. That's what we're going to have on this exam. So this one will probably finish today. We'll probably finish solutions today. And then after that, we will go ahead and we'll start our next chapter, which will be on chemical reactions. If you want to do our review session, let's honestly, let's just do it during spring break, I guess. Doesn't really matter to me, so might as well give you guys the extra time. So let's do the review session on Thursday the 1st. Yeah, that should work. That is going to be 4/1, April Fool's Day for your review. How funny. I'm going to trick you guys, give you all the wrong information. Okay, so just like always, put your questions in Discord before that. Your homework will be due for solutions on the 28th. It's this homework is not very long, relatively speaking, compared to some of your last ones. This one, it's kind of like you do a simulation, so you're going to be kind of like playing with molecules and seeing how they dissolve, and various things like that. And then there's just a few questions like molarity and a couple calculations on that. So that's up right now. I put it up there, and that'll be due this Sunday. So you'll have plenty of time to look at the keys for that, and you'll have time to come up with questions if you want. And we'll just do the review session during spring break instead of this Thursday. So we'll just do that then. Figure you guys would probably want more time and maybe time to forget all the stuff anyway. So we'll see. Cool. So, any questions on kind of like the schedule, I guess, for now? And also I think the let me just double check this, but I think the like final drop deadline is also coming up. I hope it's not already passed. Let me just double check that. Where would this be? Important dates. Okay, let's see. It is the 26th, so just note that as well. That is coming up. It is the last day to drop. With your W. So, if you are considering it, I can give you some answers to questions, but it is going to be your decision, and you can talk to the counselors as well about making that decision. But I don't think there are many of you who are in danger of failing, so I think we're okay with this. I know I have a mountain of grading for you guys for your class, so but that shouldn't have a huge impact unless you've like missed a lot of homework assignments. In that case, just like email me or message me on Discord, and I'll like prioritize grading yours so you could have the most information for that decision. All right, and then we have spring break on the 29th, just so we all know. And so there will be no class that week. So I will not be streaming for you guys next week. So it'll just be spring break, except for the Thursday review session. I'm fine with that. Still COVID time, we're still no travel and all that. So plus we don't get really do spring break anyway. I have grading to do. So cool. All right. Alrighty then. If there's nothing else on that, we can kind of go back to solutions. After this, we'll do chemical reactions, and it's a long chapter, that one, so we'll have plenty of time to spend on those. And then towards the end of the semester, we'll have some time for review there as well. So, cool. Alrighty, if there's no questions, then we can go ahead and get started here. So, last time we did kind of some solubility rule stuff. We talked about that for something to be soluble, it needs to do one of three things for our class. It needs to contain one of the group 1 metals, ammonium, acetate, or nitrate. So anything with one of those will always be soluble. We don't have to worry about those. Option 2 is it can contain a halide, where we just kind of say X minus to represent any of those three halides. And then we had a couple exceptions, right? We had silver, lead, and mercury as exceptions here. Remember, X can be any of those three, whatever it happens to be. And remember that those are going to be insoluble if they are in red there. So silver, lead, and mercury halides are insoluble, whereas every other halide, cobalt chloride, iron chloride, bismuth chloride, whatever, come up with some random metals, put those with those anions, they'll be soluble. And then 3, we had the ones that contain the sulfate ion. And then we had a couple exceptions there. We had 6 of them, right? We had calcium, barium, strontium, as well as the ones from before. And then the mercury. So, everything else, anything that's not covered on this list, we are going to assume it is insoluble. So if it's not covered by this list, one of these 3 categories, we're going to assume whatever it is insoluble. So with that, let's go ahead and do a couple of examples here. So I want you guys to, while I pull up a video for us, I want you guys to tell me if these are going to be soluble or not. So you go ahead and do those 6. Try and evaluate them now using the rules that we've just come up with. And try and tell me if these you would expect to be soluble in water. In the meantime, let's go to our textbook. I have some fun videos for us today. And of course, if there's any questions, throw them out there. Otherwise, we'll just have a few minutes to work on these while I pull up the videos. I looked at that one. All right, let's see. I wanted to just show you what it looks like when you make something that is insoluble. Okay. So, hopefully you guys have had a chance to do those ones. And then if not, we'll just do them now. So you can just pause it if you like. But we should expect that cobalt 2 chloride should be soluble because it has those chloride ions on there. So remember, chlorides will be soluble unless they are one of those 3 exceptions. Speaking of those 3 exceptions, we would expect the silver bromide, wow, insolver, that's not even close, insoluble. We would expect silver bromide to be insoluble because halides of silver are exceptions to that. So anytime you see silver with one of the halides, the group 7 ions, those are going to be insoluble. Lead 2 nitrate, we're expecting that one to be soluble. We're expecting that because it has the nitrate group, right? It doesn't matter what else is in there, it's got nitrate, it's soluble. Don't even have to look at it. There's no exceptions there. Lithium carbonate. We should expect that one to be soluble as well because it has the lithium. Just like with nitrate, anything that has lithium with it will be soluble. Same with sodium or potassium. This cobalt 2 carbonate, we're expecting that to be most likely to be insoluble because we do not have a rule for either one of those. We have nothing special about cobalt, we have nothing special about carbonate, so we're expecting anything that's not covered by our list to be insoluble. And the last one, ammonium sulfide there, we should expect that to be soluble because it has that ammonium group there. So I have an example of this stuff for us. We're going to see that I'm going to take solutions of lead nitrate, lead 2 nitrate, and potassium iodide. And we're going to see that those 2 solutions are clear, but when we mix them, we end up getting out this insoluble substance of the lead 2 iodide. So we're expecting this one to be soluble, but this one will be insoluble. And so we can see what that looks like. So let me go ahead and share that window. Okay. All right, so notice these 2 solutions are clear. Definitely clear solutions here. We're going to mix them up. And you're going to see what happens. So obviously there is a pretty pronounced color change, right? And while it may not be obvious to us, remember when we talked about colloids or suspensions, we talked about those being kind of opaque. We can't see through them. They're going to scatter light. We can see here this is definitely going to be that case. We can't see through this anymore. And if you look really closely, you can kind of see little chunks at the bottom. And that's going to be that lead to iodide or what we call a precipitate. It's a solid product. So something that is insoluble in water will kind of crash out of solution as solid. And so that's kind of what we're going to look forward to next chapter. But we kind of introduce the solubility rules now, just so you can kind of have them going in your mind, and since they are related to solutions as well. And so remember here that in order for something to be soluble or insoluble, this means that the interactions are very strong, relatively speaking. So lead and iodide are very attracted to each other, and as a result, they are not going to be able to be broken by water. Whereas potassium and nitrate and all these kind of ones that make things soluble, they are very happy to go along with water, and they're very weakly held on to different things. So just remember what the solubility process is all about: comparing interactions. So we're going to see that the insoluble things have very strong attractions, soluble things have weaker attractions, respectively. Alrighty, any questions on that stuff? Alright, well, if not, we're going to talk about properties of solutions now. We're going to see that there's a lot of stuff we can talk about relating to solutions. Primarily, the first one is going to be conductivity. We're going to see that different substances, when dissolved in solution, can make a solution conduct electricity better. So let's see. I have another video for us here. Got to go back to chapter 8 though. And we're going to see that certain substances will conduct electricity when dissolved, and we'll take a look at why that is. Let's see. Actually, I think it's under this. Is this the one? Maybe it's the next one. No, I lied. It's the one before. Okay, so when we're looking at how solutions behave, let's pop open the window here. So I have solutions of a couple of different things here. We're going to see that we have a kind of variety of compounds here. One of them is deionized water. That's the one on the left. Actually, we should probably stop this because it's a fairly longer video. We don't need to have my voice going on here. So we're going to see that these light bulbs will kind of light up with regard to how much electricity can be conducted by a solution when we put an electrode through it. And we're going to see that if we have a lot of ions present in solution, those are going to conduct electricity. So we've got 3 light bulbs here just to kind of take a look at how strong our electric conducting capabilities are. Let's just skip ahead a little bit. So we should know that deionized water, water that does not have ions in it, does not conduct electricity. And yes, that is indeed superintended at Chalmers that we use as our electrode there. If we put it in tap water, notice tap water does have some ions present in it. We can tell that because it does conduct electricity, just a little bit. So that's why only that little light bulb went off. If we go ahead and look at the sugar water does not conduct electricity. We'll see how that is. Sodium chloride definitely has some conductivity. Let's try the strong light bulb. Poof, lots of conductivity there. So we have evidence that sodium chloride will break into ions. And then calcium carbonate we see does not conduct electricity, even though it is an ionic compound. And if you look closely, in fact, you can just see, excuse me, oh no, You can see the calcium carbonate is still solid at the bottom there. It doesn't dissolve. So we're going to see that even though it's ionic, it's made of ions. Because it doesn't dissolve, there are not ions present in solution there. So conductivity is all about are ions present. And we're going to see that if there are ions, then yes, we can conduct electricity. So uh, if yes, we can conduct electricity. And we're going to see that some substances will uh, behave differently when we dissolve them. We're going to see that soluble ionic compounds like the sodium chloride, we call these strong electrolytes. Let's take a look at what that word means. You probably have heard it in everyday life. If you've seen a Gatorade commercial or something like that, you'll see that they always talk about electrolytes. Or if you work in healthcare, Pedialyte is an important substance to have. Or if you have kids, in case they're having diarrhea or vomiting, just to reestablish ion balance with them. We see that electrolytes is a word we can maybe take apart. Electro refers to electricity. And if you've studied biology, you know what the suffix light means. Something that has that light ending means breaking. That comes from lysis, by the way. Lysis is breaking. And so we see that this word, electrolyte, means they conduct electricity when broken or separated apart. So if we take some sodium chloride, we're going to see that if this dissolves, we would write it as aqueous, right? Dissolved in water. Remember, that's what aqueous means. But what this actually means is because it is a strong electrolyte, and we know it conducts electricity, we know that that comes from having ions in solution. So that really means that we have sodium ions in there and chloride ions in there. So that's what it means to be a strong electrolyte, is that if you are dissolved in water, you are going to break apart into the ions that make you up. If we look at some of the other examples we saw what, lithium carbonate. That's going to break into 2 lithium ions plus the carbonate ion when we break it up, when we dissolve it. So if we put this in water, we end up dissolving our lithium carbonate, and it's going to break apart into its ions. And note here, this time we end up with 3 ions overall when we dissolve this. We have 2 lithium ions, 1 carbonate ion. That's 3 ions altogether. We would actually expect this lithium carbonate would conduct better than sodium chloride of equal concentration because there are more ions present in solution per mole. So we're going to see that the more ions you have, the more you can conduct electricity. Oh, software updates, those are the worst. However, if we look at something like calcium carbonate, if we try and put that in water, we just get nothing changing. And so this one does not conduct electricity. And so we saw that. And calcium carbonate is chalk. We know chalk does not dissolve in water. So it ends up not producing ions in solution, and so we do not see any conductivity taking place. All right, just so we're clear with this, strong electrolytes will always dissociate, that means break apart, completely in solution. So we're always going to break those up into ions in reality. And so we do see that those will conduct electricity as a result. All right, any questions on that? Strong electrolytes. So again, these are ionic compounds that are soluble. We're going to also see that we have a few other things. 6 acids are also strong electrolytes. And those 6 are going to be the ones of the halides, except for fluorine, as well as nitric acid, perchloric acid, and sulfuric acid. So these 6 acids are all going to be strong electrolytes. I'm just going to put one AQ here. All of these would be aqueous, right? And that means in solution, for example, this will break apart fully into hydrogen ions and bromide ions in solution. And I have another video for you guys to look at that in just a little bit. So if we take this and dissolve it, we will break that apart. All right, just like if it were a soluble ionic compound. We're going to see, actually, let's just make the distinction now, I suppose. All other acids are going to be what we call weak electrolytes. They will dissolve but only dissociate. Oops. A little bit. So for example, all other acids are going to be weak electrolytes. They only break a little bit. And so we see that they only very weakly conduct electricity because there are not a lot of ions in there. There are some, but not a lot. For example, acetic acid we're going to see that as a weak acid, as a weak electrolyte, it's not one of these 6. We're going to see that maybe less than 5% of these acid molecules will break apart. In reality, it's closer to 1%. These do not typically break apart. They will dissolve, but they don't break apart like the ions do. And we're going to see that, this would be more than 95% as a result would still be as the molecules. So if you want to think about it, you have, if you were to try to take a snapshot of the solution here, Oh my gosh, let's see what's the best way to do this. Okay, I know what we'll do. Okay, so we're going to just do a bunch of these. They look like little olives. If we were to just kind of take a look at this in solution, we'll say that that blue thing is the hydrogen and the green thing is the acetate. What this will look like, oh, there we go. This is what it would probably look like in solution. Something like this. So we see most of the molecules are clumped together. There's still these little olive things, but every so often, one of them will dissociate. You know, less than 5%. So 5 out of 100 at a given time will have broken apart. So we see that only at a given time, only a small proportion of molecules dissociate. And this is, again, for weak electrolytes. And weak electrolytes are just going to be those acids. Every acid except for those 6. So hydrocyanic acid, hydrofluoric acid, nitrous acid, all of those other acids, carbonic acid, are going to behave like this, where we're going to have most of them are going to stick together as a molecule, but a few of them will break apart as ions. And so they're kind of just in between. So they will conduct electricity just a little bit. And so I have a video for you on that one as well, so we can go ahead and see that in reality here. Let's see, is this going to be, yes. Okay. So, another video, back to our conductivity experiment. So, we're going to see, okay, so again, we're going to have our water here. We're going to have some hydrochloric acid and some acetic acid. These are of the same concentration. And then we're actually going to have a very low concentration of hydrochloric acid. And we're going to go ahead and see what the conductivity looks like for this. So again, the amount of light bulbs that we can activate is proportional to how conductive they are, and therefore how many ions are present in solution. So we put it in the HCl. We definitely have some ions in there. We have quite a few ions. We see that we get a lot of electricity being conducted by that solution. Strong electrolyte there. If we put it into our acetic acid, we have some ions, so we saw a light bulb go off. If we put this one, we can kind of, you see that light bulb kind of flickering? And then let's just go ahead and put on the last one here. There's no conductivity there. So we see we have a small amount of ions in solution with that. And if we put it in a more dilute solution of HCl, we still get all those ions present. So even though there's less concentration here, it still is a strong electrolyte. And we're going to see that it strongly conducts that electricity. Okay? And so we see that these will only weakly conduct electricity as a result, because they're only a little bit broken apart. All right, and then we have the last group of substances, which we call non-electrolytes. These will dissolve, but don't dissociate. So they do not break apart at all when we put them in solution. And we saw, maybe if you remember from the previous video, we saw that we had sugar water, and it did not conduct electricity. We know sugar dissolves in water, but we saw it did not conduct. Sugar is going to be a non-electrolyte. As a result, we would say something like sugar or ethanol. These would be examples of things that dissolve but don't conduct electricity because they don't break apart. So they just kind of dissolve into the solution, but they don't form ions. So no ions are present with these sorts of things. And these are going to be mostly covalent compounds, ones made of nonmetals. So sugar, for example, is made, oops, this would be glucose or fructose or some of the simple sugars. Ethanol, something like formaldehyde. Would be another example, something that would dissolve but doesn't break apart. What else do we have? Let's see. How about ammonia? Let's not say ammonia. That's going to be a weak one. Let's say, how about what would be a good example of some other covalent compounds? To a little extent, we have dichloromethane a little bit. Can also dissolve. It's not going to break apart. Let's see, we have acetone. As you can see, most of these are hydrocarbons, right? Or carbohydrates. Carbon-based molecules typically are going to be the ones that are not going to dissolve in the water here. Or they will dissolve, sorry, but they will not dissociate. All right, and so they just dissolve and that's it. So if we take glucose here, and we add water, we still have our molecule intact. All of them are intact. They do not break apart. And we just have them as aqueous. So they're dissolved in water, but they don't break. So they are non-electrolytes. They do not break apart to conduct electricity. And we saw that with the example of the, I think we used a sucrose that time, but it's the same process here. All right, so kind of in summary of this, okay. We're going to see that we have the three categories. We have strong electrolytes, weak electrolytes, and non-electrolytes. These will all be things that dissolve, and they differ in their dissociation. So if it dissociates completely, that means all of the molecules or all of the ions break apart completely. That's a strong electrolyte. For a weak electrolyte, they only partially dissociate. And then for a non-electrolyte, they do not dissociate. And so that's kind of the spectrum we're looking at here. So ones that completely dissociate are strong. Things that don't at all dissociate are non-electrolytes. And then in that middle is the weak electrolytes, where some of them will break apart. A proportion of the molecules will break. And those are going to be what we call weak acids that we'll talk about later on. And so that's kind of the difference here. And so strong electrolytes will conduct electricity strongly, weak electrolytes weakly, and then non-electrolytes will not conduct electricity. And so that's what we see here. All right. So let's take a look at some examples. Of course, we should have kind of our last category, which would be things that don't dissolve at all. And so those would not be classified as any sort of electrolyte because they don't dissolve. So there's no, if it doesn't dissolve it, you can't classify it as any of these things. All right, so if we go ahead and take a look at a couple of examples here. We can do a few. Let's see. What would be another example? Well, some glycerin there, and then how about some how about we put also zinc bromide. Okay, cool. So with these, if we're going to classify them as electrolytes, we want to predict how they will dissolve. So we're going to see that if we can kind of identify the classes of these things, we can predict what type of electrolytes they are. So if we look at sodium phosphate, that's an ionic compound, right? It's got metals in it. It's an ionic compound. We're expecting it to dissolve because it has sodium. If an ionic compound is soluble, it will always be a strong electrolyte. All ionic compounds that are soluble are strong electrolytes. All right. Sulfurous acid, we'll say, is the next one. If we want to think about sulfurous acid, we have to consider if that's one of our 6 acids. And if we scroll back up to those, we have 6 acids that are strong electrolytes, and all other acids are weak electrolytes. Actually, we have that written here. So, do we see sulfurous acid in this list? H2SO3? It's not here. It's not on this list, so it must fit in that category of everything else, which will be a weak electrolyte. It's a weak electrolyte because it is not one of those 6 acids. All other acids are going to be weak electrolytes. Remember, acids have the H plus on them at the start. However, if we look at sulfuric acid, that is one of our strong electrolytes. It is one of those 6 that we'll want to remember. It will completely break up in solution. Barium sulfate is an ionic compound, so you might be tempted to say strong electrolyte. Excuse me. But we'll notice it is an insoluble compound. Sulfates with barium do not dissolve, and so this one will kind of just not fit in. We can't classify this one as an electrolyte, as what type of electrolyte, because it doesn't dissolve. Alright, glycerin, we may not have any clue what glycerin looks like, but chances are organic compound like this, something made of carbon, a carbon-based compound, is going to be a non-electrolyte. So you don't need to know kind of the structure, but it is going to be a non-electrolyte. So I'm only going to give you organic compounds like this that would dissolve in water. So glycerin does dissolve in water. And so we're going to see that that was going to be a non-electrolyte. Our last one, zinc bromide, ionic compound. We know it has zinc in it. It's got a metal, so it's made of ions. It should be soluble because bromides will be soluble unless they're one of those exceptions. So we're expecting that to be a strong electrolyte as well. All right. Any questions on those ones? All right, so you'll want to be able to take a molecule or a compound and determine what type of electrolyte it's going to be. And we're going to see that that's going to play into our next kind of category here. And so we're going to see that with solutions, the other property we're going to kind of look at here, they do not boil or freeze at normal, I don't want to say normal, at the boiling point or melting point of the pure solvent. So, we know H2O freezes at 0. But if we throw NaCl in there, salt water, that we will in fact have this freeze below 0 degrees. And we see other ones like vodka here, ethanol and water, would freeze also below 0 degrees Celsius. It's in fact less than 20 degrees Celsius, negative 20. Your freezer, by the way, is around negative 20 Celsius. That's rough freezer temperatures. And so we're going to see that, we can have these solutions that freeze well below their normal freezing points. And so, this is not really, I mean, if you live in Tehachapi, maybe, I don't know if they do this there, but if you live in a place that has snow or ice on the roads, they'll often sprinkle calcium chloride onto it because that will actually trigger the ice or snow to melt. Because a solution made of those will actually freeze at a temperature below the normal freezing point of water. So you can get away with having lower temperatures but still not have solid ice on the roads, and which of course, as we know, is hazardous for driving. So we're going to see that we can do some calculations with all this fun stuff. And perhaps you know this, or perhaps you don't, but we're going to see that water boils at 100 degrees Celsius if you're at sea level. But if we put salt water, that one actually boils above 100 degrees Celsius. And so we're going to see the same thing here. So that solutions tend to expand the range that they're in the liquid state, if that makes sense. So they're going to both lower your freezing point and raise your boiling point. So we call these freezing point, depression goes down, and boiling point elevation. Actually, let me just put elevation on that side. Oops. Boiling point elevation would be another property of this. So your freezing point goes down, your boiling point goes up because of the forces that are happening here. So when water is interacting with salt, it's happy, it's going to take more energy to break those bonds, just like before. So it's the same idea here. And with freezing point, these things tend to like just interfere with the dissolving process. We're going to see that these are collectively referred to as what are called colligative properties, meaning they will depend on solute concentration. So you can't just say, oh yeah, salt water will freeze at -3 degrees Celsius. It will depend on how much salt is dissolved in your water. The more salt you have, the lower your freezing point will get. So they're called colligative. And so we're going to see that we'll be able to calculate these. And so we're going to have some equations to use here. We're going to see that we're going to have three things here that we're going to deal with. We're going to see if we kind of dissect this equation. We have the change in the freezing or boiling point. Oops. We have the molality of the solution, molality, which is going to be moles per kilogram. And then we've got two kind of special things. We have K, which is going to be a constant, and that's unique for each solvent. And our last thing is this I business, which is called the Van't Hoff factor. That's the one we don't know quite yet. I should maybe make this a little bit clearer. For this, we're going to see that I is equal to the number of particles this solute will break into. So, for example, if we break our calcium chloride, because it's a strong electrolyte, we're going to see that this will have an I of 3. 1 calcium, 2 chlorides, that's 3 total particles we get out for every particle of calcium chloride we put in there. If we put in aluminum, sulfate, we're expecting I to be 5, because we have 5 ions total. If we take a look at sodium chloride, that breaks into 1 sodium, 1 chloride, I would be 2. We break 2 particles up. If we take a non-electrolyte like glucose, we see we just get 1 particle out. So we put 1 particle in, we get 1 particle out, we have an I of 1. For sodium chloride, we put 1 thing in, we get 2 ions out. Aluminum sulfate, we put 1 thing in, we get 5 ions out. And so we're going to see that all non-electrolytes I will equal to 1. For strong electrolytes, it'll be the number of ions that come out. And while we're not going to necessarily work with our weak electrolytes when we talk about this stuff, I'll just kind of put that out there. Our weak electrolytes will have an I somewhere between 1 and 2. So it'll be somewhere in there. And obviously, it could be 1.1, it could be 1.2. It just depends just how much it tends to dissociate. And so that's something we're not going to deal with this sort of calculation. We're going to just do ones that have I's of integer values that we can work with. However, unfortunately, it does look like we are going to be out of time, but I can go ahead and... let's just do this tomorrow. So this is just the last part of this chapter, so we'll go ahead and just finish it off tomorrow, and then we can start talking about chemical reactions. So, cool. Any questions on any of the stuff we've gone through today? Again, it's mostly conceptual. We'll do these calculations tomorrow, and so we can work with those. Okay, yeah, looks good then. If that's the case, I will see you tomorrow then, I suppose. So enjoy the rest of your Monday.